Welcome to the first in a series of training exercises given here at the National Weather Service in Birmingham. I'm meteorologist Kevin Laws, and today I want to review hailstorm characteristics using a variety of warning decision tools. This will be a review, and many of you will already know the subjects that we're going to talk about. But first we want to understand the properties of VIL and VIL of the day and how each relates to reflectivity structure. Second, we want to identify the different components of the hail detection algorithm and how each is calculated at the RPG. And finally, the biggest thing we want to try to do is increase situational awareness of hail by looking at things like upper air soundings, and in particular, what is favorable and non-favorable for hail formation. Okay, let's get into VIL. It seems like no matter what, VIL always seems to be a part of our lives when it comes to warning decisions. Every single time that I've been a warning forecaster, or people new have come into a warning situation or whatnot, VIL always seems to be a topic of discussion. Whether it be VIL of the day, what VIL was with this storm when it had this type of hail that was reported, and so on and so forth. You know, most of you probably know exactly what I'm talking about. But what does VIL really mean? How does it calculated? What is VIL of the day? And what are we really, talking about when we say, what is VIL? A little bit of background about it. It was implemented with the original WSR 88D package back in the early 90s. And believe it or not, it was originally designed to give you column precipitable water content. In other words, it had nothing to do with hail at all. It was just trying to give you PW values for each pixel that you see there on your screen. However, after they started getting into it and testing it a little bit, they realized that it didn't work. But what the calculation was actually integrated reflectivity. So in other words, from the top of the storm down to the surface, it was nothing more than just integrated reflectivity, exactly what you see there on your screen as you go into your all tilts and go up and down in the storm. Then something strange happened. Some people down in Central Florida wrote a paper back in 1993 that started comparing VIL to hail and hail size. Well, that just sent everybody off to the races. This paper was really not based on a lot of science per se, but everybody's off to the races, and there's absolutely no putting the lava back into this volcano. Now we're forever going to associate VIL with hail. So in that way, I call VIL the ultimate Frankenstein, because it was really originally designed to do something that is totally different than what we anticipate it to do today. Well, there it is. That's VIL as an equation. A lot of people are scared of equations that look like this, especially ones that have this old crazy integrand in them. But I tried to put it into a sentence there, a color-coded sentence, and really VIL is the sum, that's the integrand, from the ground to the highest elevation scan of reflectivity factor, not reflectivity, multiplied by the distance between two adjacent scans. We'll get into that just here in a little bit. How about some important VIL facts when the calculation is made? Fact number 1, any values less than 18 dBz are removed. That's for obvious reasons. They don't want to include anything that may be bugs or any other anomalous propagation that's on the radar. A big one, anything greater than 56 dBz is truncated to 56 dBz. Okay? So normally we think of hail as having large dBz values or reflectivity values. Those are not even included in the calculation. So if you look at the radar scope and you see a 68 dBz and you say that has to have some ice in it, keep in mind that our fallback product VIL is not even using 68. It's using 56. It is a grid-based product, which means it's based on the grids that you see from the radar instead of individual storm cells. And it is averaged out to a 4x4 kilometer. That's why it looks so much bigger than the original 8-bit reflectivity values. And the data values range from 1 to 70 kilograms per meter squared. So notice that that it is in kilograms per meter squared. Again, going back to the precipitable water. And here's the scale. Obviously, most people are familiar with it. And that's why it's in every 5, because it is a 4-bit product. Again, the resolution 4x4 kilometers. Okay, so as the radar scans, and this is just some sample scans, we go up, and remember the equation. So in between each height it is calculated, or reflectivity factor is multiplied by the difference in height. Taking a closer look, a couple of unique things about the integran. First, from the 0.5 elevation scan, which would be the bottom one here on my sample, down where the red indicator is, down to the ground. So no matter where that 0.5 scan is, if the 0.5 scan is at 10,000 feet, 5,000 feet, it doesn't matter. It's always integrated down to the ground. So if your first scan, if your 0.5 scan is a very high number, say 50 dBz, that's being included all the way to the ground. So there's a potential that that integran could be 10,000 feet, 5,000 feet. So that really makes a big difference on your final VIL number. Another biggie too is that a lot of the calculation could be below the freezing level, particularly if you're really close to the radar. So the closer you are to the radar, the more scans you have below the freezing level. So you're actually calculating dBz that could be below the freezing level. And again, you're trying to use something like that to calculate something for a hail size or hail yes or no product. What do I mean by cell-based and grid-based? Well, as a cell-based product, and believe it or not, there is such thing as a cell-based VIL. It's calculated at the RPG. You can't find it on the menu anymore. I think you can probably pull it up and scan if you tried, but it is there. But again, the way we see it now and the way it's traditionally used is that it's a grid-based VIL, which is the bottom right image here. And you can see if a storm is tilted, as in our example here, or if a storm is moving very fast, then your VIL could be spread out over several pixels instead of it being calculated for one pixel, versus a cell-based VIL where you get one VIL for one storm, as long as the SCIT algorithm is working correctly. Okay, let's take a look at an example. This is from April 11, 2007 in central Alabama for a particular storm here, and I've shown each of the heights. The radar was in VCP 12 at the time, so here is 9 scans up to the top of the storm. Don't worry about seeing each individual ones because I'll show them to you as we move along here. But you can definitely see many three-body scatter spikes indicating that there was definitely hail in this particular storm. Here is the reflectivity as you go up into the storm. So on the left we have height from 0 up to 45,000 feet, and then reflectivity across the bottom. So you can see right away that 60 dBz, there is a lot of scans, a lot of reflectivity above 60 for this particular storm. In fact, it goes all the way up to about 35,000 feet, including down at the surface. The lowest scan was 76 dBz. That's one of the highest dBzs I've seen before we had the super resolution product. Okay, so now you see all of this 60 and 76. What would you think the VIL number would probably be for a storm like this? Probably pretty high. Here's the VIL for that same exact storm. Notice that the highest VIL I can crank out of this is 55. Now, we've all seen VILs that are higher than that, 60, 65. A lot of warning criteria are based on that. You can say, well, it's not quite 60 VIL, so I'm not going to warn. With this particular storm, even though it had a 76 in it, and all 60, above 60 dBz up to 35,000 feet, I could only get 55 out of this storm. What happened? That's not what I want to say. Okay, let's take a look at the same storm from a different radar perspective. So before we looked at the Birmingham radar, now we're going to look at Maxwell, which was seemingly a lot closer. An interesting thing about Maxwell was that it's right next to the, I'm sorry. Let me start that whole thing over again. Let's take a look at the same storm now from Maxwell radar, which was a lot closer to the storm. Interesting here, first of all, is that Maxwell was actually in 121 that day. I've never seen one of our radars here in central Alabama in 121, so maybe we were having some range folding issues. But nonetheless, here are 9 scans from the bottom to the top. The very bottom right-hand one is 19.5. And you can see, again, 3-body scatter spikes in a lot of these scans. Same image from Maxwell. Now notice we don't go as high because Maxwell is so much closer. But again, every single level is above 60 dBz. Just like with the other storm, now our VIL is only 35 kilograms per meter squared. So we've gone from 55 to 35. So depending on which radar you're looking at, you have VIL of this storm of 55 and from Maxwell 35. Here are the two next to each other. Okay? So from BMX radar we have a 55 VIL. From Maxwell we have a 35 VIL. See, I'm almost thinking I need another slide in there because I need to explain why. Okay, here is the chart for comparing both storms. Here is a similar chart comparing both storms from each radar. Oh, that's not right. One storm from both radars. Shut up, Gary. Okay, here is a chart showing the same storm from both radars. As you can see, BMX had a higher VIL because it had more volume scans to look at, while Maxwell, which was... Sorry, I don't know what I'm going to say about this yet. Don't worry, I can cut all this out, Gary.
What is it you're trying to say? If you just say it like talking plainly you're hearing, maybe you can.
Yeah, I need to go all the way back actually. I'm missing some stuff that I really want to include. Okay, let's take a look at an example. This is from April 11th, 2007 for a storm in central... This thing gonna be horrible or what? I'm gonna have to edit this thing all day.
Well, I mean, everybody makes mistakes anyway, so.
Okay, let's take a look at an example of a VIL. Jesus Christ. Okay, let's take a look at an example from April 11, 2007 for a storm in central Alabama. The radar was in VCP-12, and you can see the 9 scans we had from the Birmingham radar. Many of these scans are showing the purples and the whites indicating above 60 dBz, and there are 3 body scatter spikes, so you know this storm definitely had some hail indicated with it. Maybe a little tough to see the color scale, but don't worry. This chart should show you exactly what we had in that storm from the bottom to the top. The left-hand side shows the height from 0 to 45,000 feet, and along the bottom we have reflectivity. Notice that for a bulk of the storm up to about 35,000 feet, we're above 60 dBz, so this is a pretty healthy storm. In fact, down at the lowest elevation scan, we had a 76 dBz, which is one of the highest I've really ever seen before we had the super resolution output. So just by looking at this, you would anticipate that we should have very, very large VIL numbers. In fact, with this storm we didn't. The most I could squeeze out of it was 55 dBz. So what really happened? Well, it turns out as you go up into the storm that the reflectivity, going back, the reflectivity is not in one column. So in other words, I'm showing you cell-based reflectivity. So since it's not vertically stacked on top of each other, the VIL numbers are spread out through the storm. Where you see the highest VIL, 55, is where it obviously had some of the deeper reflectivities. But again, the 76 number was not even included in the calculation for the 55 VIL. Thinking back to what we talked about though, 76 wouldn't even be included. It would be truncated back to 56. So theoretically, it doesn't matter that you even had a 76 in there. So is 55 dBz a real good indication of what kind of hail or hail size you might expect from this storm? Again, just using VIL alone may get you in trouble in a warning scenario, because some people may be looking for 60 or 65 vil before they put out a warning, and indeed in this case we only had a 55. And this is, again, the maximum I could get out of the storm. Looking at the same storm from a different radar perspective, the Maxwell radar was a lot closer. By the way, Maxwell was in 121 this day. Kind of unusual. I've never seen our radar in 121. So we may have been having some range folding issues. But here are 9 scans. This is from the bottom to the top again to 19.5 is the bottom right. Again, 3 body scatter spikes. There's plenty of reason to warn on this storm. But again, we're just looking at the VIL. Reflectivity wise, this is from Maxwell. Again, we're only up to about 18,000 feet because it's so close to the radar. But again, every single reflectivity in the maximum reflectivity was above 60. Most I could squeeze out of it, VIL on this storm was 35. So again, we have 55 and 35. Comparing the two storms, not a lot of VIL shown from this. So what really happened this day? Well, indeed we had softball-sized hail there reported in Macon County at about this time that we were looking at. So from a 55 VIL and even a 35 VIL, we only had softball-sized hail. So that's obviously pretty significant. What happened with Maxwell? Why did we only get 35? Well, it's obvious that it was too close to the radar, so you don't have enough levels to really get a good integration and get a high enough number. So 2 different problems for exactly the same storm. Again, Maxwell, too low, too close to the radar. You're not sampling the full amount of the storm. You're not getting enough in your integration, so your VIL calculation is only running up to 35. Birmingham, plenty of height on the storm. You can see almost up to the 45,000 foot, so it's seeing the entire storm. But a different problem in that the reflectivity was not vertically stacked right on top of each other, so your VIL numbers are going to be biased low. Okay, what about VIL of the day? This came out of VIL and developed and modified through the early 90s. Most of it was in 1993, again from that paper I mentioned at the beginning from Central Florida. It has taken on many forms throughout the years. Most people today use it as a number 750 divided by the temperature at the 500 and 400. So you just take the nearest sounding. You get the average temperature between 500 and 400. You see it's divided by 2. So it's a layer temperature. And you take 750 divided by that. Now, where does the 750 come from? Well, believe it or not, that's just through trial and error. So 750 is just an arbitrary number through trial and error. Looking at a sounding from that particular day of the storm we looked at, again, you're taking the 500 and 400 temperatures, as you see there, and I've actually got a VIL of the day calculated at 37. So in this particular case, the VIL of the day did work for if you're looking at the Birmingham radar. However, it would not have worked, say you're looking at the Maxwell radar for that particular storm, even though you had softball-sized hail, some of the largest hail you'd see in our area. So on this particular day, the VIL of the day turns out to be 37. Again, I said it takes on many different forms. I've seen it where you just only use the 500 temperature. But the big thing about VIL of the day, the important point is that you're only looking at pressure levels. Okay, so no matter what the sounding is, you're always looking at the same 2 levels. Okay, I didn't want to skip over digital VIL. A lot of people have a lot of questions about digital VIL. How is it different? What's so unique about it? Digital VIL actually used exactly the same equation. Some important facts about digital VIL now. Any values less than 18 dBz are included. So now we're including all values less than 18 dBz, which is different than VIL. Aha, another big one. Values greater than 56 are now used in the calculation. So the immediate question is, that I normally get is, why is digital VIL so much higher than regular VIL? Well, it's mostly because now any DBZ is included in the integran. It's also the same as a grid-based product. Its resolution, though, I'm sure you've all seen it and know that the resolution is now 1 degree by 1 kilometer. So in other words, it is the true 8-bit. However, they did something strange with this one, and that the data values are only from 0 to 80. So now, even though you can include anything over 56 dBz, you can't get any measurement over 80. They stop it at 80, and that's an FAA thing, requirement. And that's the reason that happened. I have petitioned Eric Howison and some other folks at the Warning Decision Training Branch about getting this changed to an open-ended scale so we can actually see what the true calculation is. Here's a picture of that same storm, and you can see since it maximized at 80, you don't get any more detail with digital VIL. And again, this is compared to regular VIL. So you saw 55, now we're maximized at 80. What do you think the actual digital VIL was, since it's more since it's more grid-based and a little bit better resolution, and we could include things like the 76? Well, it turns out the digital VIL for this particular storm was about 315. So that's a pretty high number compared to the VIL that we saw in Legacy VIL, which is which is 55. Okay, what are some uses of digital VIL that I've noticed? Let's take another storm. This is not the same storm, but it's a different storm on the same day up in Coosa County, which is just to the north. You can see our storm down to the south. As this storm in Coosa County moves along, one thing I've noticed about digital VIL is the resolution. Since the resolution is a little better, you can actually see storm structure, like different updrafts in the storm. So if a storm is splitting, and this storm is splitting to the north, you can start to see indications of an updraft forming to the north of the main core. In this case, you can see across central Coosa County the main core, but then notice to the north that you can see a new core that is developing. As time goes on, this core continues to develop. This is something that you wouldn't see in VIL, but digital VIL shows it pretty well. Okay, on to the HDA. Okay, HDA has several outputs. First one is the probability of hail, the POSH, which is probability of severe hail, maximum estimated hail size, and what else can you get from the HDA? You can get the freezing level and -20 level, and what time it was last updated at the RDA. Each one, how does it calculate it? PO, I'll be honest with you, is not that useful. Okay, it's based on a step function. So as you get higher, as the 45 dBz gets higher in the storm, the probability of PO gets higher. So you think about as you look up into a storm, where is that 45? It goes and picks out the highest level of the 45 and gives you an output. So there's not a lot of science involved in it. POSH, however, is a lot better. It uses the numbers that the RPG from 0 and -20 degrees Celsius, or what some folks consider the maximum hail growth zone. It calculates a minimal probability when the 40 and 50 dBz cores are above the freezing level. However, it turns into a maximum probability once they get above the -20. So unlike VIL of the day, instead of using pressure levels, it actually used heights that are actually inputted by the user. So you have some environmental parameters that are put into the POSH. So just like VIL of the day, it looks at where these cores exist. If you have a core that goes above the freezing level, it gives you a certain output on probability. If that same core gets higher, so it knows where the -20 is, as that core gets higher, the probabilities will really shoot off the charts. So you actually have some environmental information that you're able to use with POSH. The final output is the maximum estimated hail size. Generally speaking, the hail size are not very representative that we've seen. Most of them are overestimates. Where did they get these from? Well, it was a Northern Plains hail study. So what they said was, okay, we have a certain core in this storm. Let's go to a lookup table and look up what size we had with that storm. So basically, it's just you're looking at a lookup table. So it's just giving you a rough idea of what the maximum hail size may be in a storm. Going back to what we were talking about with POSH, you can see here the 0 and -20 highlighted by the red. So again, it's based on the particular sounding versus being based on a pressure level. So as the sounding changes, these numbers will change as well. So as a core of a storm gets going and moves up into the above the freezing level and then again above the -20, our POSH numbers will really increase significantly. Let's look at the Birmingham radar, our storm from before. Remember, our Ville numbers were only 55. But looking up at the chart, we see a couple things interesting. First of all, the freezing level is at 11.3 thousand feet, or 11,300. The minus 20 level is at 21,000. So our maximum hail growth zone above the freezing level is pretty large, from 11,300, and then again above 21,000. You can see our size here is 350, so it is close to softball size hail, and our Posh and Poe are both 100%. The O2 is just a storm ID, the same as the skit, and what you see is a colored in triangle on your screen, and the 4 is giving you an estimated value of the maximum hail size, so it's just rounded up to 4 in this case. Okay. The fact that the triangle is big and colored in means that the Posh numbers are actually above 50%. Okay. How does this work with the Maxwell radar? Well, not quite as good. The Posh numbers are only 50. I'm sorry, this is F3, so the Posh numbers are actually only 30 for softball size hail. But again, same as Ville, Posh can't overcome the fact that the storm is so close to the radar. Okay, maximum estimated hail size on this one is only 1. And believe it or not, the Poe numbers are only 30 again, but remember, it's a step function. And remember, the radar can only see this storm up to 18,000 feet. So since you don't have anything above 18,000 feet, it just thinks that the storm is short, and it's not going to be a problem for you. So again, you have to be careful even when using things like the hail detection algorithm in cases like this. Okay, from our study that Scott Unger and I did last year, we looked at about 360 cases of how Posh worked with a hail size distribution. So in other words, taking a look at, for example, the black line here, those are all hail sizes that are non-severe. And check out, as the probability of severe hail gets higher and higher, the number of reports goes further and further down. So that's kind of a good sign that if you have a Posh of about 100, 90 to 100, the probability of you getting a bad report, or a non-severe report, is going to be fairly low. However, when you have the red, which is the bottom line there, which is greater than golf ball size, it's very unlikely that something that size is going to be in the 50, 60, or 70 Posh. It looks like it starts really increasing once it gets to 80, 90, and especially 100 there. Same thing for the moderate size hail, the 1.25 to 1.75. Once you get above a 60 Posh, it really increases significantly. So we're fairly confident that once you get above, say, a 70 Posh, that you're probably looking at severe hail in a lot of cases. As always, though, the difficult size to detect is that size that's just above severe, up to about quarter or half dollar size, that 0.75 to 1.25, the green line at the top, and it's really all over the place. Again, look how many number of reports we had in that size range, and it's really all over the place. You can have a 50 Posh and have that size, or 100, and it's about the same distribution. So again, nothing is foolproof, but just know that it looks like to us from this study that it's going to be very difficult to miss, say, some of the larger hail events, just based on the HDA itself, or the hail detection algorithm itself. Okay, what about some strategies as a warning forecaster? Some facts. Ville is a great two-dimensional tool to examine overall changes to the three-dimensional reflectivity structure. Okay, if you're busy and you're having to keep an eye on radar out one eye, Ville is not a bad product to have up. Okay, you can immediately see changes on a two-dimensional field. So instead of having to scan through the full tilt, volume tilt of a storm, Ville can automatically tell you, hey, this storm is either increasing or decreasing. Now, you don't necessarily know if it's above or below the freezing line in the concern of hail, but at the very least, you'll know, since it's integrated reflectivity, you will know that the storm is either strengthening or weakening just based on the Ville, as long as the storm is moving slow enough. By utilizing the hail detection algorithm, you offer freezing level and maximum hail growth information to storm cells that are in question. Okay, the fact also that HDA is cell-based instead of grid-based it doesn't matter that the storm cells are moving fast as long as the skid is determining that the storm is actually there. So it's good for fast-moving scenarios, which is typical sometimes in the southeast. And one more important fact, that the higher resolution digital VIL provides some information as where the largest cores reside in the storm, as well as, again, new cores that could be forming. Because of its resolution, the 8-bit resolution, you can see a lot more detail than you could with the legacy VIL. Some points that are now fiction. Using VIL unilaterally can be dangerous, since you don't have any three-dimensional information. So if your VIL is high, it could be because most of your reflectivity is below the freezing level. Okay. Another important point is, even after the VIL of the day is established, you still don't know where the strongest cores are located within the storm in question. So let's say you establish that your VIL of the day is 50. You have a storm that's 55, but the storm cell is 55 because most of the core is below the freezing level. Well, does that mean there's hail in the storm? Maybe, maybe not. So you still have to question even after you've established your VIL of the day, because again, VIL is a two-dimensional product. So you don't know what the core looked like. You have to do some further examination on it. Any kind of tilted or fast-moving storms reveal false information. Think about the example I showed from the Birmingham radar, where you had a 76 dBz, 60 dBz all the way up to 35,000 feet, but your VIL is only 55 because the storm is either tilted or too fast, and VIL couldn't integrate it correctly. Digital VIL will have that same problem. Could be even worse because it's an 8-bit product. So anytime there's tilted or fast-moving storms, you're going to have some false information that you need to examine. Okay, let's go to situational awareness by looking at some severe hail soundings. Okay, first thing that's important in situational awareness is to understand the hail growth zone. Most of the scientific community says that the most favorable hail growth zone is between -10 and -30 degrees Celsius. Notice it's not freezing. It's all the way up to -10 because you have some issues of grapple and maybe some melting hail or whatever between the 0 to -10. So the maximum hail growth zone between -10 and -30. Low-level lapse rates are important to storm development and growth. However, lapse rates in the hail growth zone, again, where is it? The -10 to -30, are favorable for large hail growth. Any kind of deep layer shear, not only good for tornadoes, good for updraft strength and sustainable updrafts. Okay, so any kind of shear that you have in the atmosphere will sustain updrafts and keep them stronger. And finally, something we haven't talked about a lot is the freezing level and wet bulb heights. This has to do with melting below the freezing level. So the higher the heights are of the freezing level or the wet bulb height, the more you may have melting effects. Let's take a look at a sounding from Corpus Christi. First of all, just looking at the cape, it's around 3,000. Not too bad. That's a pretty good cape. The shear is pretty good here in this case. About 30-35 knots from 0 to 6, so you have good shear. The mid-level lapse rates are pretty decent. You can see around the hail growth zone, which is the -10 to -20. The lapse rates are pretty decent. They're not quite dry adiabatic, but they're not moist either. So overall, the threat here, and by the way, the freezing level is 12,600. So overall, the threat here would be pretty high. The cape shear combination is good. The only thing is not too great. I'm gonna start this slide over. Okay. You guys digging this? Are you understanding it?
Yeah.
You sure you're understanding? Okay. Okay, let's take a look at this first sounding here from Corpus Christi. You can see right off the bat that there is a pretty decent amount of cape here, 3,000 joules per kilogram up to the equilibrium level. There is decent shear. Notice the winds, there's a lot of turning with height and some speed shear as well. The mid-level lapse rates are okay. They're not dry adiabatic, but they're certainly not moist adiabatic either. And the freezing level is rather high, which you'd probably expect in Corpus Christi. What's the overall severe threat of hail? That's pretty high. The Cape and the shear combination is pretty good. The only thing keeping it from not great are those mid-level and upper-level lapse rates in the hail growth zone. But certainly the shear and Cape should make up for any deficiencies that you have there. How about a sounding from Alaska, where the freezing level is way low? A lot of people really hang their hat on freezing level numbers as their only situational awareness tool. Notice here that this freezing level is 5.7. Cape is not so good, even though the lowest lapse rates down in 800 millibars down to the surface look pretty steep there. A lot of the mid-level lapse rates are not that great. You can see most of it are moist adiabatic, especially in the hail growth zone. The shear is okay. It's between 25 knots, but it's unidirectional. So even though a freezing level of 5.7, the overall threat of severe hail would be none in this sounding. It'd be tough to get any severe hail, especially with those lapse rates like they are aloft, and with low Cape and shear only being decent. It's a good point about this sounding too, is that since the freezing level is so low, that non-severe hail is certainly not out of the question. How about from Hawaii now? Looked at Alaska, now Hawaii. Cape is not bad, 1350. You wouldn't expect a lot of large hail in the tropics, but that is pretty good Cape for a tropical environment. Deep layer shear is pretty weak here. You got some backing and veering aloft. There is a 60 knot westerly wind at 11 kilometers. That is impressive again for the tropics. And some of the mid-level lapse rates are kind of decent. It is moist adiabatic from about 10 degrees Celsius and above. So the low-level lapse rates are good. Here the upper-level lapse rates are okay. Freezing level in this case is about 12,000. I'd say that the threat here is only slight. It's unusual to have a thermodynamic profile like this in the tropics, but since the Cape is very large and there is some decent lapse rates, I think severe hail would even be possible in Hawaii. How about one from Nashville now? The Cape is good here. It's about 2100. Shear is pretty good. We don't have the full wind profile here. It is unidirectional though, which could make a little bit of a difference. But the one big thing about this sounding is you see the low-level lapse rates are pretty good, but look at these upper-level lapse rates, especially once you get into the around the -5 level higher. Notice how these lapse rates are really tilted to the left, and they're almost dry adiabatic or nearly. I don't know what word I want to use there. Do you understand what I'm going through these soundings? I need to go all over. I need to go through these soundings once again. You gotta go?
No. I just want to do that. You go on.
Yeah, give me 10 minutes.
I would expect one of them pistons.
What the hell is he talking about?
Are you trying to figure out a word for the lapse rates? Is that what you were?
No, it's super unstable. There's a word I'm looking for, but I can't quite grasp it. It's okay.
Super adiabatic?
No, it's something unstable. Absolute unstable. That's it. Okay, absolutely unstable.
Yeah.
Gary, you should know this stuff. What's wrong with you? Okay, let's take a look at a sounding now from Nashville, and this is a good example because of the lapse rates here in the hail growth zone. First of all, the Cape is good. It's around 2100. There is some deep layer shear 60 knots, but it is all unidirectional, as you can see. How about these lapse rates, though? Look at the lower level lapse rates first. They're pretty good. They're around dry adiabatic. But look around the -5 degrees Celsius and above. these lapse rates are really tilted to the left, so they're not even really moist adiabatic at all. They're almost dry adiabatic, so there is a lot of cape to be had up in the maximum hail growth zone. So the freezing level is 12,200, and you would expect this to be high. This is a no-brainer. Every ingredient's there. The cape, the shear is fine. And again, those upper level lapse rates are something that really need to be paid attention to. Okay, one more quick peek at our sounding from our storm. Today we had softball size hail. If you modified this sounding, again, this is the morning sounding from 12Z, so you have that, the morning, I'm getting tongue-tied on my words there at the end. Okay, one more quick sounding. This is from the April 11th, the same storm from the morning of the storm that we had, the softball size hail. And quickly you can see that this is a fairly good sounding as well. This is a morning one, so I had to modify it for the afternoon's high temperatures, so you can see that morning inversion down at the lowest levels below 900 millibars. But take a look at the lapse rates aloft, especially in the hail growth zone. Again, very steep lapse rates. Check out our shear, so you have this not only decent flow aloft, you also have the directional change. So again, this is a very good indication that you're going to have some severe hail. So a lot of people just look at the morning soundings for things like tornadoes, but again, just paying attention to the lapse rates themselves and how much cape is generated at the -10 to -30 levels, you can really tell if you're going to have a severe type hail day. What were the SPC outlooks for that day? We were in a slight risk, and the top one is the morning outlook, and you can see we were in a 15% probability for severe hail. And notice how that changed as the day went on after we started getting reports. So the slight risk increased a little bit to our west, and they've also increased the probability of severe hail from 15 to 30 in that bullseye area. So again, another way to increase your situation awareness is to definitely take a look at the individual SPC outlooks, which I'm sure most of you do as well. Okay, where did the future of this go? Well, over the next year, I'm going to be looking at something a little bit different. I'm going to look at ordinary pulse type thunderstorms and seeing how enhanced vertical motion from the rotating updrafts can really make a big impact on things like hail and sustained updrafts. So in other words, any rotation in the upper levels of a storm or small rotation within the updraft can really act to sustain the intensity and longevity of updrafts, which could regenerate hail to the core of the storm. In other words, you can have multiple cycles of hail up through a storm if you have an intense enough updraft. So I'll be looking at that over the next year. How about future training, mini training modules here? We got a couple coming up that are going to be understanding MOS products, ZR relationships and how they're used at the RDA. How about a nice review of supercell characteristics, the different types? Like I said before, the impacts of rotating updrafts. And finally, I'll do one on some split cold fronts and cold fronts aloft at the very end. So I hope you've enjoyed this training module and gotten something out of it. Have a great day.